Imagine standing beneath a midnight sky, staring up at the same stars our ancestors did centuries ago. One of those stars, burning bright in the shoulder of Orion, has always stood out, a massive crimson beacon known as Betelgeuse. It has shimmered with mystery, a cosmic giant on the brink of death. For decades, astronomers have known that something was coming. Betelgeuse, a red supergiant more than 700 times the size of our Sun, has long been unstable, pulsing, flickering, dimming in irregular fits, as if gasping for breath. But no one could say when the inevitable would strike. Then, without warning, it happened. The James Webb Space Telescope, perched silently in the cold void beyond the moon, captured something no one was sure we'd ever see, the beginning of a supernova in real time. Not a theory, not a simulation, not a historic remnant. But the live, violent unraveling of one of the universe's most colossal stars. This isn't just another data point for astrophysics. This is a generational event, perhaps the closest supernova humanity will ever witness. Only 642 light-years away, Betelgeuse is practically in our galactic neighborhood. And when it erupted, it didn't just change the sky, it changed our understanding of the universe. What the James Webb Space Telescope saw wasn't a single explosion, but an ongoing, chaotic transformation. Layers of Betelgeuse's atmosphere are now peeling away. Its once balanced convection currents are collapsing into erratic bursts of thermal energy. Enormous plumes of gas, each the size of planets, are being flung into the cosmos like ghostly echoes. On the star's surface, bubbles bigger than Jupiter burst and vanish in seconds, releasing energy that travels faster than anything we've ever observed from such a dying star. For the first time, we are watching a stellar collapse not as a concept, but as a lived moment, frame by frame. Betelgeuse isn't just ending. It's becoming something else. Its massive core, once holding back gravity with the force of nuclear fusion, is now imploding. And as that collapse begins, a chain reaction spreads through the star's outer layers. The James Webb Telescope's infrared sensors have peeled back those layers, revealing a landscape of destruction more intricate than anyone predicted. Magnetic fields, once aligned across thousands of kilometers, are now twisting and tangling into violent knots. Particles accelerate in chaotic spirals, emitting signatures never before recorded in stellar observations. Somewhere within this violent chaos, a shockwave is forming, a growing ripple that will detonate through the star's envelope and eventually send its outer shell blasting into space at millions of kilometers per hour. Webb didn't just catch this moment. It's watching it happen in real time. The implications are staggering. Because Betelgeuse is so close to Earth, cosmically speaking, we're not just seeing light. We're seeing mechanisms. Physics once thought impossible to observe directly are now playing out right in front of our instruments. We can see how convection currents collapse. We can observe how gas escapes from the star's surface in turbulent, spiraling jets. And deep within the light curve, scientists have begun to detect patterns, signatures of heavy elements like oxygen, carbon, and iron being synthesized under crushing heat and pressure. These are the very elements that build planets. That built us. And here they are, being born in real time within the body of a dying star. It's as if we're witnessing the DNA of the cosmos being written before our eyes. What's even more staggering is how bright this explosion is expected to become. When Betelgeuse fully erupts, its light could outshine the full moon. For weeks, maybe months, we might see a second sun hanging in the sky, an eerie, brilliant monument to the violence of stellar death. But brightness is only part of the story. Scientists are far more interested in the rare chance to measure a supernova so close, using every instrument we've developed over decades. The Webb telescope has already begun capturing shockwave activity moving through Betelgeuse's expanding shell. Each wave carries information: how hot the plasma is, how fast it's moving, what elements it's carrying, and what particles are being released. These shockwaves, as they crash into the interstellar medium, are literally shaping the space around the star, pushing aside dust clouds, heating gases, and perhaps even triggering the formation of new stars in nearby regions. This is the universe's ultimate recycling program. A star dies, but in doing so, it spreads the seeds for new solar systems, new planets, and potentially new life. Betelgeuse's death is not an end. It's a beginning. And for the first time in human history, we're not just theorizing about this cosmic cycle, we're watching it unfold. Every day, new data pours in from Webb, from ground-based observatories, and from space telescopes tracking other wavelengths. Together, they're building the most complete picture ever assembled of a star's death. And buried in that data are revelations we never expected. For example, the discovery of gravitational perturbations, minute but detectable shifts in the fabric of spacetime itself, rippling outward from the collapsing core. If these are verified as gravitational waves, then Betelgeuse becomes not just the first visible supernova of its kind, but the first to be directly tied to spacetime distortion, a moment where Einstein's theory and visual astronomy collide in a single, historic event. This would fundamentally rewrite our understanding of how stars affect the universe. Up until now, we've believed that most gravitational waves come from black hole mergers or neutron-star collisions. But a supernova producing them, especially one so close, means our models need revision. It would suggest that even as it dies, a massive star can send out ripples through the universe that touch everything, including us. This isn't just poetic. It's measurable, and it's redefining the limits of what our tools can detect and decode. And there's more. As Betelgeuse unravels, the Webb Telescope is uncovering new behavior in its dust halo, a cloud of cosmic debris that surrounds the star like a tattered cloak. This halo is shifting, reshaped by radiation and shock. Where there was once a relatively smooth spread of dust and gas, there are now cavities, ripples, filaments, structures sculpted by the star's last gasps. This means Betelgeuse's death is also a sculptor, carving the local space environment in ways that could eventually influence the formation of new stars, or even planetary systems, in the distant future. We are standing at the edge of something profound. The death of Betelgeuse isn't just a story about astronomy. It's about connection. About understanding where we come from, and how the atoms in our bones were forged in the hearts of stars like this one. Through the lens of the James Webb Telescope, we are witnessing our past, written in the language of light and gravity, and our future, illuminated by a dying star's final gift. This is not the end of Betelgeuse. It's the beginning of a new chapter in human understanding, a moment that binds us more deeply to the cosmos than ever before. And the story has only just begun. As Betelgeuse collapses under its own immense gravity, it reopens one of the most profound mysteries in astrophysics: what is left behind when a star of such magnitude dies? The possibilities are staggering. Could it become a neutron star, one of those ultradense remnants formed by tightly packed neutrons? Or perhaps, does it go further, succumbing entirely to gravity and forming a black hole, a region of space so warped not even light can escape? Yet now, with the most recent data streaming in from the James Webb Space Telescope, another, even stranger possibility emerges, one that defies conventional categories. Webb's instruments have detected anomalies in the collapse, magnetic field irregularities, plasma voids in the ejecta, and what appears to be asymmetric fallback, material that should have escaped into the vacuum of space, inexplicably curving back inward toward the dying core. This odd behavior has led some astrophysicists to suggest something truly revolutionary, a transitional object, an entirely new category of stellar remnant that exists in the blurry boundary between neutron stars and black holes. A hypothetical form that has been discussed in theory, charted in simulations, but never directly observed. And now, perhaps, we're watching the birth of this cosmic anomaly in real time. If this is confirmed, Webb's data could represent the first observational evidence of a brand new class of celestial object, something that changes the very taxonomy of the universe. But as with any event of this scale, a question begins to echo through public discourse: are we in danger? Betelgeuse, after all, sits a mere 642 light-years away, a blink in cosmic terms. Could a supernova so close pose a threat to Earth? The immediate answer is reassuring. No, we're not in danger. The explosion, as violent and magnificent as it is, occurred far enough from Earth that we are shielded from its most destructive effects. However, the long answer is more nuanced, more layered. The detonation has released a vast shockwave of high-energy particles, including streams of gamma radiation and expanding bursts of electromagnetic energy. While they won't scorch our atmosphere or extinguish life, these waves can disrupt the fine structure of cosmic dust clouds drifting through the galaxy. They can alter the dynamics of nearby star-forming regions and subtly shift how light from distant galaxies reaches our telescopes. Even the interstellar medium, the thin gas and dust that threads between stars, can be reshaped by such an event. As Webb monitors the velocity, density, and expansion of the radiation front, scientists are preparing for potential observational side effects. For even if Earth is physically unharmed, the very way we see and understand the cosmos may be forever changed. The lens through which we've studied the heavens for decades could soon be distorted, bent slightly by the invisible hand of a dying giant. Betelgeuse, once a beacon in the Orion constellation, was one of the brightest, largest, and most studied stars in our sky. Its life spanned millions of years, burning through stages of stellar evolution with increasing instability. And now, it ends, not with a fade into darkness, but with an incandescent death that sends shockwaves across both space and science. But what Webb has captured isn't just the death of a star, it's a moment of cosmic reflection, a celestial mirror held up to humanity. It reminds us that even stars, those ancient points of light we often associate with permanence, have lifespans. They are born, they evolve, they age, and eventually, they die. In that death, however, lies a paradox: something ends, yes, but in its ending, new elements are born. The crucible of a supernova forges materials that no planet can produce, that no laboratory can simulate. In the violent heart of Betelgeuse's collapse, temperatures and pressures soar to unfathomable levels, fusing atomic nuclei and casting them outward into the galaxy. These elements, carbon, iron, oxygen, even the building blocks of DNA, will drift through space, perhaps to become part of a planet, a tree, a human heartbeat. Betelgeuse's destruction is not annihilation, it's creation on a cosmic scale. It's renewal. It's the cycle of the universe, and we are lucky, immeasurably lucky, to witness it in such detail. And in that detail, another astonishing revelation emerges. As Webb analyzes the spectra of the ejected material, it detects surprising anomalies, not just the usual suspects like carbon or iron, but far rarer elements like technetium and yttrium, substances that can only be formed in the extreme nuclear chaos of a dying massive star. These exotic isotopes are fragile, short-lived, and rarely detected, making their presence here all the more astounding. Their abundance provides a crucial window into the internal processes of supernovae, like fingerprints left behind at the scene of a cosmic explosion. But more than that, the ratio of these elements allows scientists to piece together the life cycle of matter in the galaxy. These atoms will travel for millions of years, embedding themselves in dust clouds, enriching the chemical composition of interstellar space, eventually becoming the seeds of future solar systems. It's a story that stretches across time and scale, from the core of a star collapsing in silence, to the molecules that may one day power life on another world. What Webb has done is not simply capture an explosion, it has cracked open the code of how matter, and by extension, life itself, comes to be. And Betelgeuse, in its last moments, has given us a lesson in cosmic alchemy, a final, generous act of stellar storytelling that began long before Earth formed, and will echo long after we're gone. As the cloud of debris expands outward, Betelgeuse will fade from the sky. The familiar red dot in Orion's shoulder will be no more. In its place will be a nebula, an expanding veil of gas and glowing dust, lit from within by shock waves and radioactive decay. But that visual absence will be replaced with something much greater: knowledge. Betelgeuse's death gives us more than spectacle. It gives us data, insights, evidence. It grants us a glimpse of what our own sun might experience billions of years from now, albeit on a smaller scale. It's a chance to prepare, to understand, to marvel. The light that reached us from Betelgeuse traveled 642 years through the cold emptiness of space, carrying with it the story of its own demise, like a letter written by a star we could only read after it had already gone dark. And in that letter are revelations that challenge and expand our sense of time, of physics, of possibility. Because without supernovae, there is no complexity. There are no planets with oceans, no rocks with iron cores, no atmospheres rich in nitrogen or oxygen. There is no Earth, no life, no us. We owe our existence to stars like Betelgeuse, ancient giants who lived brilliant, unstable lives and died magnificent, explosive deaths. And now, thanks to Webb's unmatched sensitivity, we are finally seeing the process unfold with such clarity that it feels almost intimate. The raw materials of everything we are, our bones, our blood, our breath, were forged in moments like this. We are, quite literally, watching our own origin. In the silent void, where time slows and stars live their final days, Betelgeuse has left behind more than dust. It has left behind questions. What truly lies at the heart of this event? Could Webb's instruments reveal gravitational echoes, the subtle warping of space that hints at a black hole being born? Could neutrino detectors on Earth pick up the ghostly remnants of the fusion processes deep within the dying star? Could the shockwave ignite surrounding clouds and trigger a new generation of stars? The possibilities stretch out like constellations waiting to be connected. We are not just spectators to this event, we are participants in its unfolding consequences, tasked with making sense of what it all means. And so, as Betelgeuse's light fades, something extraordinary has happened. We've crossed a threshold in human discovery. We've moved from wondering about our place in the cosmos to reading the instructions the cosmos itself has written. In the final burst of a distant red giant, we saw more than fire, we saw a map, drawn in the language of physics and time. We saw the birth of future worlds. This isn't just the end of Betelgeuse. It's the beginning of an era where stars no longer die in silence. Now, we hear them. We see them. We understand them. The James Webb Space Telescope has changed everything. And what comes next, what other secrets the universe still holds, may reshape science in ways we've only begun to imagine. Because beyond this one fading star lies a sky filled with billions more, each with its own story, its own life, and eventually, its own brilliant end. We're watching the universe write its history in real time. The question now is, are we ready to keep reading?